All right. Hello, everyone, and welcome to this online tech talk on encrypting secrets in Amazon EKS. My name is Pavan Mistry, and I'm a senior developer advocate in AWS Container Services team. I've spent 5 years at AWS as specialist solutions architect in security and compliance, and as a senior technical program manager with AWS Security. Prior to this, I've been a security consulting leader and developer at global enterprises. In my current role, I work with AWS Container Services product teams to inform developers and evangelize container services features and product deep dives to our customers. I've put my email address and Twitter handle on this slide, so feel free to contact me through email or Twitter anytime for any questions on AWS Container Services, container security, or AWS security in general. So this is a level 300 Tech Talk, so understanding of AWS and Amazon EKS is expected. First, for context, we'll quickly understand the fundamentals around the Kubernetes secrets. Next, we'll do a deep dive into how secrets are secured in Amazon EKS. And at the end, we'll learn of the key management options within AWS Key Management Service, or KMS, and the value each option provides for your Amazon EKS cluster secrets. I have a demo to accompany each of these topics as well. The goal of the Tech Talk is to leave you with an understanding of Kubernetes secrets within Amazon EKS and how AWS KMS can help. This will help you make an informed decision to secure your cluster secrets and meet regulatory and compliance requirements for your EKS workloads. We'll end the Tech Talk with a Q&A session. So, secret is a very broad term these days, and there are several solutions. So let's narrow down the scope of this tech talk to ensure it meets your expectations. The secret reference in this tech talk is limited to Kubernetes Secrets object in Amazon EKS. So it's not AWS Secrets Manager, it's not AWS Systems Manager Parameter Store, and it's not any other secrets management solutions available from AWS Partner Network. In particular, we'll be talking about this issue, which is on the screen from AWS Containers Roadmap, which was closed in early March 2020, when we launched Envelope Encryption of Kubernetes Secrets in Amazon EKS. To accompany this feature, our engineers, Gyho Lee and Rashmi Dwarka, and my colleague Michael Hausenblas wrote an excellent blog post to introduce and explain the value of this feature. All right, so let's understand some fundamentals to set the context around the Kubernetes secret object and how it is stored in Amazon EKS cluster's control plane. To help us do that, let's start with a difference between encoding and encryption. So the purpose of encoding is to transform data so that it can be properly consumed by a different type of system. The goal is not to keep information secret, but to ensure that it's able to be properly consumed. Encoding transforms data into another format using a scheme that is publicly available so that it can easily be reversed. It does not require a key as the only thing required to decode it. It is the algorithm that was used to encode it. Some of the examples are ASCII, Unicode, or base64. Whereas the purpose of encryption, on the other hand, is to transform data in order to keep it confidential. Rather than focusing on usability, the goal is to ensure data cannot be consumed by anyone other than the intended recipients. Encryption transforms data into another format in such a way that only specific individuals can reverse the transformation. It uses a key in conjunction with the plaintext and the algorithm in order to perform the encryption operation. So it introduces this problem of keeping the key secret. Some of the examples include AES and Blowfish as symmetric algorithms. Okay, so in this quick demo, let's look at base64 encode and decode of the string plaintext. We have the Python code on the top left for base64 encode and bottom left for the base64 decode. So when we run this script, So when we run this script, we get a base 64 encoded result out of the message plain text. And when we feed that outcome to the decode script within the other screen, let's have a look. And it returns the plain text. Now let's take a look at the encryption example quickly. I have a KMS customer master key with alias Tech Talk KMS HSM. It is the key with which we want to encrypt the plain text. When we run the encrypt code on the top left, let's have a look at what it returns. Right, so here we have the ciphertext which was returned by the script, and when we feed this into the other code and run a decrypt, we get the plain text again. However, for every encrypt, it's going to return us a different result, which is the ciphertext, which is not the same as the previous one. So if you take this ciphertext again, and feed it into the decrypt algorithm, it's going to return the plain text again. So note that we didn't need to send the key details to decrypt. The ciphertext in itself was sufficient enough for the algorithm to return us the plain text. So if you were to encrypt multiple plain text values with the same key, the key then becomes really important. So we introduced the concept of data key or data encryption key, which is every plain text has its own key to encrypt with. And to protect the data key, we use a master key to encrypt the data key with and store both the encrypted data key and the ciphertext together. And this is known as envelope encryption. So this is a visual representation of envelope encryption that I just described. So to reiterate, envelope encryption stores the encrypted data key and the ciphertext of that data together. In AWS KMS, the master key is referred to as customer master key, and it is also referred to as key encryption key or KEK in other places. There are several benefits of using envelope encryption. It scales with the number of messages you encrypt, as we just saw with the data key introduction. You can encrypt very large messages with very little transmitted data. You can limit the scope of a single data key as it only helps decrypting that particular piece of plain text, which it is attached to. Data key can be cached and used across multiple messages, so it reduces calls to AWS KMS and also reduces latency. So now that we have learned the fundamentals around encoding and envelope encryption, let's take a look at how this is all relevant to Kubernetes Secrets object. So Amazon EKS is a fully managed Kubernetes service that runs upstream Kubernetes and is certified Kubernetes confirmant. EKS provides a scalable and highly available control plane that runs across multiple availability zones to eliminate a single point of failure. Now, talking of control plane, it consists of etcd, which is the default Kubernetes Secret object store. Kubernetes Secrets objects let you store and manage sensitive information such as passwords, OAuth tokens, and SSH keys. Storing confidential information in a secret is safer and more flexible than putting it in a pod definition or in a container image verbatim. So users can create secrets, and the system also creates some secrets. To use a secret, a pod needs to reference the secret. However, by default, in Kubernetes clusters, the secret stored in etcd is base 64 encoded. When you use Amazon EKS, by default, even without the envelope encryption feature, all of the data stored by the etcd nodes and associated Amazon EBS volumes is encrypted. Amazon EKS uses master encryption keys that generate volume encryption keys, which are managed by the Amazon EKS service. Now let's jump to a demo to take a quick look at an Amazon EKS cluster, and let's create a secret. All right, so initially, let's have a look at how many clusters are there in my region in the EKS environment. So I have 3 clusters here. One is without secret encryption, and the other 2 are with secret encryptions with a different CMK store. I use an alias for my kube control, so replace the K with kubectl if you're doing it on your terminals. And the current context for my config is without secret encryption. So right now, all the commands I'll be running are on that on that cluster. So I'm going to create a generic secret from a literal username. Ideally, you won't be doing this because you're passing the secret in plain text here. Rather, they'll be supplied through a volume, or you'd be providing a file through which you can create the secret. But for ease of use here, I'll be creating a secret quickly in this cluster. So once we have created the secret, let's get the secret. And as you can note, the information is base64 encoded. Now, since we don't have access to etcd, I'm unable to show you the details around how this secret looks on etcd, which should be base64 encoded. So let's jump back to the presentation. So the threat to inform your threat model is if an attacker gains access to the Kubernetes control plane or masters, or in particular etcd, they run this command using etcd control as shown on the screen and have access to base64 encoded secrets in your Kubernetes cluster. That introduced the problem or the threat, and now let's take a look at the mitigation or the solution. Kubernetes community have kindly created KMS Encryption Provider, which uses an envelope encryption scheme to encrypt data in etcd. The data is encrypted using data encryption key. A new data encryption key is generated for each encryption, and the data encryption keys are encrypted with a key encryption key, or KEK, also known as customer master key in AWS KMS, that is stored and managed in a remote KMS. The KMS provider uses gRPC to communicate with the specific KMS plugin. And there is an open source project called AWS Encryption Provider that integrates with AWS KMS. So with this, let's take a look at how it all works when you read and write a secret to your Amazon EKS cluster, which has secret encryption enabled. So in this diagram, we have the user who is going to create a secret and pass it on. When they do a create secret, they'll pass it on to the API server. So API server gets a request, and when that write request for the secret comes in, the API creates a data encryption key and it stores it in the DEC cache. Along with that, the key is encrypted using the secret, is encrypted using the data encryption key in memory. Now, since we have a new data encryption key for envelope encryption, it needs to be encrypted using a master key, as we saw in the previous demo. So the plugin, the KMS plugin, AWS Encryption Provider, calls KMS and asks it to decrypt or encrypt the DEC with the customer master key. So there is an encrypt call going out to AWS KMS, which returns the encrypted DEC using the CMK. Now, that gives us both components of envelope encryption. One is the secret, which is encrypted with the DEC, and the DEC, which is encrypted with the KMS CMK. So that completes the cycle around creating the envelope encrypted secret, and it's then stored into etcd. Now that's the right secret flow. So when a new secret is created, it gets encrypted using this flow. And now we'll take a look at how the secret is read within this plugin. So when a user goes and creates a get secret request to API server, there is a check to find whether the data encryption key is already in the cache, and if it's in the cache, then it calls up the etcd cluster, etcd key store, and it pulls in the secret encrypted using DEC, and using both of these, the end result, or the secret, is provided back to the user. And when the data encryption key cache doesn't have the key within it, it calls in the Decrypt function using the KMS plugin for AWS Encryption Provider, and then it makes a decrypt request. The decrypt request then returns the decrypted DEC using KMS CMK, and then now since we have both the DEC and the secret encrypted using DEC, the secret is then returned to the user. So one thing to note is that since the KMS CMK is in customer's account, you should define the access policies according to your cluster administration and operational design to allow roles and users limit access to CMKs based on least privilege and need to know security principles. So the calls made to KMS are logged in CloudTrail, and they are presented as a CloudTrail event. So the Encrypt CloudTrail event is shown on the left of the screen, and the Decrypt event is shown on the right. One thing to note in particular is that because of the existence of cache, the secret read calls to Kubernetes API server will not generate Decrypt event in CloudTrail if the DEC exists in the cache. So let's say you have a new secret which was created, and you make a read call right after creating the secret. That means it will have the DEC in the cache, and you won't see subsequent decrypt calls in your CloudTrail event. Now let's take a look at the key management service as it encrypts and decrypts the data encryption key using CMK. So AWS KMS provides a web interface to generate and manage encryption or cryptographic keys, and operates as a cryptographic service provider for protecting data. AWS KMS offers traditional key management services integrated with AWS services to provide a consistent view of customers' key across AWS with centralized management and auditing. AWS KMS is a secure and resilient service that uses hardware security modules that have been validated under FIPS 140-2 or are in the process of being validated to protect your keys. AWS KMS is integrated with AWS CloudTrail, as we just saw, to provide you with logs of all key usage to help meet your regulatory and compliance needs. It also includes operational aspects as you'd expect from KMS, which is around security, durability, availability, auditability, latency, and throughput. So you can create multiple CMKs, each represented by its key ID. You can define access controls on who can manage and or use CMKs by creating a policy that is attached to the key. So the customer master keys, they represent the top of key hierarchy, and they never leave the KMS or the HSM. They have a unique ARN, and they are non-exportable, as I just said. They are generated on HSM or imported by the customer. So there are several options there for customers, region-specific and globally unique. Now, KMS has 3 key origin alternatives that help meet Amazon EKS customers' key management requirements for secret encryption. The external or bring your own key option that you might use if your organization has any of the following requirements. So if you want control on your key and how it was generated using the entropy of sources, or you want to keep your own backup copy of your existing key material and upload keys only when you need them. So if any of these requirements are within your workloads that you define, then external or bring your own key is the option. AWS CloudHSM is a cloud-based hardware security module that enables you to easily generate and use your own encryption keys on the AWS cloud. With CloudHSM, you can manage your encryption keys using FIPS 140-2 Level 3 validated HSMs. CloudHSMs offer you flexibility to integrate with your applications using industry standard APIs, such as PKCS11, Java cryptography extensions, JCE, and Microsoft libraries as well. CloudHSM is standards compliant and enables you to export all of your keys to most other commercially available HSMs. It is a fully managed service and enables you to scale quickly by adding or removing HSM capacity on demand with no upfront cost. So in my usage, I could add an HSM cluster fairly quickly, in probably about 20 minutes. So you may have the same experience depending on your location. So you might use CloudHSM or custom key store option if your organization has any of the following requirements. Key material that you would want to use cannot be stored in shared environment. Your key material must be backed up in multiple AWS regions, or if your key material must be subject to a secondary or independent audit path, or the HSMs that generate and store key material must be certified FIPS 140-2 at level 3 overall. So if your Amazon EKS workloads need FIPS 140-2 validated HSM hardware at an overall level 2, then AWS KMS HSM would help you meet that requirement. So essentially, there are 3 alternatives for you with different requirements that you may come up for your EKS workloads, and KMS would help you align with those and satisfy those with your external auditors or your security teams. And that brings us to take a quick look at the FIPS 140-2 validation for both KMS and CloudHSMs. You may ping me on Twitter if you like, and I can provide you with the links to these public documents on FIPS validation for both KMS and CloudHSMs. And it's also at the end of the presentation. All right, so let's take a look at these key origins within KMS in action on the console this time, and we'll also take a look at cluster creation YAMLs using EKS control and look at how you can create these clusters on the console. So here we are on the console of EKS, and we can see there are 3 clusters running Kubernetes version 1.16. One cluster is without secrets encryption enabled, and the other 2 are with secrets encryption with a different key origin. So the one with KMS HSM is a cluster running with KMS Key Origin, and it provides you the link to the KMS key. So I'm going to click on the KMS key, and before you're concerned, these clusters will be removed and deleted and doesn't store any confidential information. So when we click on the KMS key ID, it takes us to the KMS console and shows us the cryptographic configuration where we see the origin as we just saw in the slide previously. So the origin is AWS KMS, which means that the CMK or the master key through which the DEC or the data encryption keys are encrypted is stored within the KMS HSM, which is FIPS 140-2 validated at level 2 overall. And now if we go back to the EKS service and look at our clusters, particularly the one with CloudHSM, which uses custom key store, then we'd see that it has a different KMS, which brings us to KMS again, but this time the cryptographic configuration is with origin AWS CloudHSM, and that means that the CMK, or the customer master key, through which the data encryption keys are encrypted when that KMS encrypt call is made, is using CloudHSM or stored within CloudHSM. Now, CloudHSM has a cluster ID and also has a custom key store ID. So let's take a look at the custom key store ID. And it's backed by a couple of HSMs here. And let's look at the cluster, which brings us to CloudHSM. And that cluster has 2 active HSMs with both in different availability zones, which is the requirement for establishing a custom key store. So your clusters need to have, your HSM, Cloud HSM clusters need to have at least 2 availability zones with HSM each within them. It automatically sort of creates daily backups for you and has monitoring functions and tagging functions as well. So that's a quick review around the source, or the CMK sources through which you can encrypt your secrets. And obviously the one without secret encryption does not have any KMS key attached to it. Let's quickly look at how you can create a cluster using secrets encryption enabled. We have recently improved the user experience here. So I'm just going to create a test cluster, or at least just show you how you would create a test cluster. Select the version. And then if you want to enable secrets encryption, which I would highly recommend that you do, you are given an option to create or select one of the KMS keys. So we can select one of those keys and click next, which will bring us to creating that cluster. Now there is another simpler way, provided that you have created the KMS keys already. You can use EKS Scuttle to create the cluster real quick. And here I have some of the examples where I have created these clusters with the secrets encryption enabled. What you would provide to EKS Scuttle or EKS Control is that YAML file, and that would create the clusters automatically after a few minutes in terms of whatever secret you'd like, as in whatever CMK you'd like from KMS. Hopefully that provides you with some understanding around how to create clusters using secret encryption. One thing to note, using the previous example around CloudTrail events, is you'd see that every time a secret is encrypted or decrypted outside the API server cache, the CMK usage is logged. So in this case, you can see on the left we have the KMS HSM key, which was accessed as the API call. And then on the right, you can see the CloudHSM custom key store, which was used to decrypt the secret. So you can integrate this with your monitoring solutions and provide visibility to your security teams or monitoring teams around how the secrets are being used within your cluster. So if you'd like to get hands-on with this and try it out yourself, we have EKSworkshop.com, which is our training site, which we have created with several examples. And within the beginner section, there is a chapter around encrypting secrets with key management service. If you have additional inputs or would like to see anything different, you can just raise a PR or an issue on the GitHub site. It's an open source site, so feel free to interact, and I'll be happy to take your suggestions. And so to summarize, why encrypt Amazon EKS secrets using AWS KMS? First of all, you'd like to secure your Amazon's EKS Kubernetes secrets from unauthorized access. There might be regulatory, security, or compliance requirements you have to align with within your organization. So you would you'd use this alternative to encrypt your secrets. You would have particular key origin requirements. You would want to manage the key operational lifecycle from service like KMS, as shown on the screen, which we've already discussed. So these are some of the reasons why you would encrypt your secrets rather than keeping it base 64 encoded on etcd key value store. So just to recap, we looked at Kubernetes secret storage in Amazon EKS, how it's stored using the base 64 encoding. We looked at the KMS plugin and understood the secret read and write flow using the KMS plugin, the AWS Encryption Provider. Looked at benefits of encrypting secrets using KMS and the various key origins through which you can encrypt those secrets. So hopefully that provided you with some insights into how it works under the hood, and we are working towards integrating with AWS Secrets Manager. We are evaluating that as an issue. So if you have any thoughts or ideas, do try to put in your requests or suggestions onto our containers roadmap, and we are constantly sort of listening to our customers. And here are some of the resources that we've mentioned, I mentioned during my presentation. So feel free to access those and take a look at the cryptographic details white paper in particular, which has some interesting details around how KMS operates on a technical level. There are various examples on EKS encryption, using EKS control encryption cluster, and also the containers roadmap. So feel free to ask me any questions you have on email or using Twitter, and I'll be happy to answer your questions. But that's all from me for this tech talk, and thank you very much for attending and listening to it, and I'll open up to any questions you may have. Thank you.